I am Amit Kumar from Bhaskacharya College of Applied Sciences, and I am going to present a paper entitled Analyzing Zinc Sulfide Quantum Dot Suitability for Optical Applications. If we compare quantum dots, they have shown many advantages over the traditional semiconductor, including compact size and high speed of operations. The electronic confinement within the quantum dots are able to be controlled in a number of ways, which attract many engineers in variety of new applications. The simulation studies in these fields are very important as it allows scientists to study before they experiment. In the present study, we simulated and examined various optical properties of zinc sulfide quantum dots, such as absorption spectra, polarization-induced changes in the light, and intra-band transition intensities. The simulations were done using NanoHerb's Quantum Dot Lab. When we simulate a typical 9.5 into 10 into 10.5 nanometer cuboid quantum dot of zinc sulfide, for the first 8 energy states, we get 8 orbitals size like this. As you can see, the ground state is much similar to the s orbital, where the next 3 states are showing dumbbell shaped orbitals and next 4 are showing d orbital type electronic distribution. The optical transitions, there are many optical transitions possible in between these 8 states, but out of which only few are allowed. For example, this allowed transitions are also dependent upon the polarization of incident ray. For example, when we talk about X polarized light, the transition which is much more dominant is present here and here, and it refers to S to Px transition at the energy of 0.0388 electron volt. But when light incident is Z polarized, then there are 2 transitions present here and here, and these are referred to, corresponds to Px to dxy transition and Py to dx to y2 transition. So we can infer that the absorption is much more dependent upon polarization of incident light. It can be also evident from the angle of incidence. As the angle of incidence changed from 90 degree to 0 degree, we can see that there is when theta is 90 degree, there is only one peak. When theta is 0 degree, there are 2 peaks. So this shows that the absorption by the quantum dots are very dependent upon the angle of incidence and the polarization of the incident light. It is also dependent upon the temperature. As we can see that when the temperature is very low, at 1 Kelvin, there is no peak, there is only a single peak. But when the temperature is around 400 Kelvin, then there is a existence of 2 peaks. These peaks are referred to be because of the quantum confinement of the electrons within the quantum dots. Generally, these peaks are evident in the bulk semiconductor when the temperature is very low, but in quantum dots, these excitonic peaks appear even at the room temperature, and this confirms the quantum confinement of the electrons within the quantum dot. The Fermi level dependence is also there. You can see that when the Fermi level is coinciding with the LUMO level, it is written here, EF is 0 electron volt. So this refers to when the Fermi level coincides with the LUMO level, then there is a high absorption, and as the Fermi level moves away from the LUMO level, the absorption drops. This is because of the fact that the electrons, as the many electrons will be present near the Fermi level, then there will be more absorption, and the absorption decreases as the as the Fermi level moves away from the LUMO level. Quantum dots also show high dependence on the shape. We can see here that for a typical quantum dots, in a different shaped quantum dot, the peaks show different positions, and it is because of the fact that high surface area shaped quantum dots show higher absorption than those quantum dots whose surface area is less. Absorption is also dependent upon size. As the different sizes are there will be a shift in the peaks, as evident from this table. This shows a cuboid quantum dot of 5 nanometer, 10 nanometer, 15 and 20, and these are the 8 states. So as we change the size of the quantum dot, these energy levels also shifts. The quantum dot absorption spectra is also dependent upon the materials. We majorly discuss the zinc sulfide quantum dots, but if we use different types of quantum dots, then they show different behavior and different energy due to different energy structure. In conclusion, we can say that the presented research simulation shows the effect of wide range parameters such as size, shape and substance on the polarization of light and the Fermi level, geometry and orientation of the quantum dot along the axis and absorption spectra. The obtained results also show very wide adaptability to the size and material over infrared range. Various quantum dot devices such as infrared laser, long-range communications and night vision cameras can be plugged over the large range using these kind of materials. These are some of the references that I have used in this study. Thank you very much. Namaskar.